All right, good morning. This is Math 1314. It's March the 5th. A couple of announcements. Web-assigned homework is due tomorrow. I did postpone it originally from March the 4th to give you a couple of extra days. Sections 5.2 and 5.3 are due tomorrow, March the 6th. The next couple of sections, 5.4, 5.5, are due on March the 18th. It's March the 18th because we've got spring break coming up next week. So you get a little bit extra time to do that homework. Exam 2 review, I have it, I think, about 99% done and maybe 100% done. I have to just go back through it one more time to make sure it's ready to go. I put a lot of time in on it last week. And so I should be able to post that either later today or for sure by tomorrow, Tuesday. So be looking for Exam 2 review to be going up on my Google site pretty quickly here. Remember that spring break is next week. So next week, no lecture. No lecture at all on Monday or Wednesday of next week. I will be available for appointments. So if you do have, for those of you who are with me today live and those of you who are watching this recorded later, if you do want to meet with me in my WebEx room during the week next week, there will be some times when I can do that. You just need to email me or send me a remind message, one or the other, and we can try to work out a time if you have some questions that you want to go over. I'll be happy to try to meet with you next week during spring break. So please take advantage of that. All right, today, basically the first half of class, we will be talking about polynomial functions, and then the second half of class, we'll be talking about rational functions and making a transition from polynomial functions into rational functions. And I've got a list of things that we're going to talk about today for polynomial functions. First of all, we want to go over a little bit about something with synthetic division that does come up on WebAssign, where WebAssign asks you to divide by things like 2x plus 3 or 3x minus 4. And so I want to make sure I can show you how to do that using synthetic division, because you do have to do a little bit something different. And then we're going to talk about building polynomial functions from graphs, and actually I should add, and zeros. Two different ways where you're given a graph and you're asked to build a polynomial function based on that graph, or you're given zeros and you're asked to build a polynomial function from those zeros. Anne-Marie, you were just mentioning this. I believe this is the kind of question you were just asking me in WebAssign. So we're going to go over a couple of examples there to hopefully straighten some things out. Then we're going to talk about the intermediate value theorem and the conjugate zero theorem having to do with irrational zeros and imaginary zeros. So we'll go through those things. And then we're going to go at the very end on polynomial functions. We're actually going to go through two examples where we kind of go through everything one last time and try to look at the big picture on this. And so we'll go through two long examples at the end of this discussion on polynomial functions to hopefully kind of bring things together at the end. And then that will leave us some time still, the second half of class, to talk about rational functions and get started on rational functions. We will not finish rational functions today, but we will start that by looking at graphs of rational functions and being able to write information down about those graphs. All right, and then on Wednesday's lecture, we'll actually finish rational functions and kind of move on from there. So, all right. So let's get started. Those of you who are with me live, please stop me if you've got a question about something. I'll be happy to stop it as we go through this. All right, so the first thing is I want to make sure that you know how to divide using synthetic division by something like 3x plus 1. I need to write here using synthetic division, because we have talked about so far how you use synthetic division to divide by things like x minus 2, things like that, or x plus 3, right? So like if you took this polynomial, and we're going to do something simple, x cubed plus 2x squared minus 3x plus 4 divided by, let's say, x plus 3. That's not a hard problem using synthetic division, because you just divide by -3. Synthetically, You divide into the coefficients here, and then you're just careful not to make any arithmetic mistakes. And as you go through the arithmetic, I get that. Let's see, make sure that I copied everything down correctly. I always got to make sure I do that, and then go through the arithmetic, and that all looks okay. So the quotient here, remember the quotient is always degree one less than original. So the original one was a third degree polynomial. So the coefficients at the bottom row of the synthetic division represent a second degree polynomial. So this would be x squared minus x. Notice there's no constant term because of the 0. And then you tack on the remainder at the end, which would be 4 over x plus 3. So that's not a big deal. But you know, all of this is kind of predicated on dividing by something like that, x minus k, where the coefficient of the x is a 1. So what if it's not a 1? What if you're dividing by, for example, 3x plus 1, like we have in our problem right here? So in our problem, this is what we're doing. I'm going to write this out kind of as a division problem this way, as a fraction. Whoa. Yeah, let me clean this up just a little bit here. But 3x plus 1 is not in the form x minus k. It's not a 1x. It's a 3x here. And so what you have to do if you're going to use synthetic division on a problem like this is you have to factor that 3 out of the polynomial in the denominator. Now, notice the 3 is a common is a factor in the 3x, but it's not a factor in the 1, so that means you've got a fraction here. And so this is x plus 1/3, like that. And you can always check this to make sure it's right. 3 times x is 3x, and 3 times 1/3 is 1. And so that's correct. And so now what you do synthetically, see now notice what we have is we have two things to divide by. We have x plus 1/3 to divide by, and then we also have 3 to divide by. And so you do that in two pieces, basically. You divide by x plus 1/3 first. That's where the synthetic division comes into play. And then just divide by the constant 3. Now you don't need a synthetic division to do that. You're just dividing literally by the number 3 is what you're doing. So the first thing you do is you take your polynomial, 6x cubed minus x squared plus 5x plus 2, and you divide by x plus 1/3. And you hope that you don't have really messy gross fractions in here. Sometimes you might, so you just have to kind of stick it out if that's true. So you're dividing synthetically by negative 1/3. We're dividing into 6, negative 1, 5, 2, like that. Right? So you don't do anything different than you would ordinarily with synthetic division. You bring down the 6. Negative 1/3 times 6 is negative 6/3. But that's good. That's just negative 2. You add, you get negative 3. And then negative 1/3 times negative 3 is positive 1. You write that in the next column. You add, that's 6. And then finally, negative 1/3 times 6 is negative 2. You add, you do get 0 here, as it turns out. So the remainder is 0. So what's the answer to this division problem? Well, the answer to this division problem, when you divide just by x plus 1/3, is 6x squared minus 3x plus 6. Now remember what I said to do over here off to the side. You first divide by x plus 1/3. That's what we just did synthetically. And now you take your answer and you divide it by 3. Because remember, what we were really dividing by is we were not just dividing by x plus 1/3. We were dividing by a 3 and an x plus 1/3. So in our problem here, you take this polynomial and also divide by 3. And all you're doing is on the other side of the equation, you're literally just dividing each term by 3. This is just a constant. There's no a constant division. There's no synthetic division here. So you just divide 3 into each term separately. So 6 divided by 3 is 2. 3 divided by 3 is 1. 6 divided by 3 is 2. And that's your final answer right there. So bottom line here is synthetic division only works for that kind of division where you're dividing by something in the form x minus k, where the leading coefficient, the coefficient of the x is a 1. So if the polynomial you have is not in that form, if the polynomial you're dividing by is not in that form, which it wasn't right here, right? The 3x plus 1 was not in the right form, then you factor out that leading term, that leading factor, the 3, and that will leave you with a binomial that is in the right form to use synthetic division. You just have to do 2 steps on this division rather than 1. You divide synthetically by the x plus 1/3, and then you take that answer and you divide it by the constant 3, and then you're finished. Now, 2 things here. This does come up on WebAssign in a place or 2. Wanted to make sure you knew how to do this when you hit it with WebAssign. The second thing is I am not going to ask you a synthetic division problem like this on an exam. On exam 2, this will not come up, just so you know. So that should be good news. All right, so that's done with synthetic division. Our next polynomial, our next problem is what we're going to do is, and you do have some WebAssign questions like this, I believe, and I definitely might ask you a problem like this on a test. Let's build the polynomial function from its graph. All right, so here's the graph of the polynomial. And what we want to do is we want to actually build the polynomial from the graph that we have here. So notice from the graph, a couple of things to look for here is, one, you have these x-intercepts. You have an x-intercept at -3, 0. You also have an x-intercept right here at negative, let's see, that's halfway between -1 and -2. That's -3/2, 0. And then you finally have another one over here halfway between 0 and 1. That's at 1/2, 0. So those 3 x-intercepts suggest, don't just suggest, they tell you that you've got zeros for this polynomial at x equals -3, x equals -3/2, and x equals 1/2. In addition, the 0 at -3 in particular looks like a parabola, right? Right in there. This one looks like a parabola at the 0. And because it looks like a parabola at that 0, what that means is at -3 you have a 0 of multiplicity 2. Now conceivably it could be a multiplicity 4 or 6, but what we do is we try to write these polynomials with least degree. So we always aim for the least degree possible. So because that one looks like a parabola at that 0, that means that the 0 is a 0 of multiplicity 2. Now the other 2 zeros look like lines. And the graph looks like lines as you go through the 0, as you go through the x-intercept. Because they kind of look like lines, those are linear factors. Those are not zeros of multiplicity at all. Okay, so we've got to start to our polynomial now from these zeros. Because remember what we talked about in lecture last week was the factor theorem. And the factor theorem stated basically that if x equals k was a 0, that x minus k is a factor. Right? Those two things go hand in hand. And really, you could even say this, that k0 is an x-intercept. Those 3 things actually kind of go together. Now, the only thing is the last one, remember, the x-intercept is only if you have a real number, right? That's if k is real. If k is imaginary, then there is no x-intercept. But for us, what we're talking about is that if k is a 0, x minus k is a factor. So what that means is x equals -3 is a 0. So that means that x plus 3 is a factor. And because its multiplicity is 2, then we know that x plus 3 squared is a factor. All right? Because we know that -3/2 is a 0, then we know that x plus 3/2 is a factor. And then finally, let's see, what do we know? We know that 1/2 is a 0. So x minus 1/2 is a factor. So we're kind of on our way here to building the polynomial. And I'm writing a lot of stuff down here. You wouldn't necessarily have to go through and write all this down. As soon as you see these x-intercepts, you know that you've got these factors. You've got x plus 3 is a factor. And because the graph is a parabola, or looks like a parabola, it's not a parabola, but it looks like a parabola at -3, 0, that means it's got to be a 0 of multiplicity 2. So you have x plus 3 squared is a factor, x plus 3/2 is a factor, and x minus 1/2 is a factor. All right, now what you don't know, so there's the polynomial right there. What you don't know, based on just those zeros, is there could be a coefficient, a constant coefficient of a in front of these factors. And those zeros don't tell you what that a value has to be. But what we do is we use the y-intercept to find a. And you do have the y-intercept in this problem, or on the graph. The y-intercept here, notice, is at 0, -27. And so what that tells you is that f of 0 is equal to -27. That's from the y-intercept. The y-intercept will always tell you what f of 0 is. So notice in your polynomial right here, okay, so what do? We built the factors, the linear factors of the polynomial from the zeros. That constant in the front you figure out from the y-intercept. You substitute 0 in for x. You have f of 0, and you literally, every place you see an x, you put a 0. So you have 0 plus 3 squared times 0 plus 3/2 times 0 minus 1/2. But the y-intercept tells you that the answer to that little calculation better be -27. And so you can actually figure out the a value from this problem right here. You have a times 3 squared times 3/2 times -1/2 has to be -27. So you have a times 9 times -3/4. I'm sorry. Put a equals there for some reason. It should just be a. So you have a times 9 times -3/4 equals -27. You get a to be -27 over 4. Well, I keep on saying a equals. I don't know why I'm doing that. Let me write that again. So you have a times -27 over 4. My voice is going away here. Equals -27. And then when you multiply both sides by -4/27 to solve for a, you just multiply both sides by the reciprocal. You get that a is 4. Boom. And you've got the a value. And so our polynomial that was sitting right here is really f of x equals 4 times x plus 3 squared times x plus 3 halves times x minus 1 half. There's really that 4 is sitting in front of that. And so, so that's actually your polynomial right there. Now, if you want to, you could actually see there's something else that's going on here that I want to point out. You have f of x equals 4 times x plus 3 squared times x plus 3 halves times x minus 1 half. And now I want to look at those kind of crazy factors, x plus 3 halves and x plus 1 half. You don't usually see factors written like that when we write out these polynomials in factored form. And so how do you make those fractions disappear in there and make those factors look a little bit more quote-unquote normal? Is what you do is you take that 4 that we just found a minute ago and you actually break it up into two 2's. And this will not just happen coincidentally on this problem. This always happens with polynomials where the integers are where the coefficients are all integers. You take that 4 and you break it up into 2 2's. And you take one of the 2's and you put it in with the x plus 3 halves, and you take one of the 2's and you put it in with x minus 1 half. So let me show you on the next screen. I'm going to copy this real quick here. And I want to, let's see, copy that. And then I'm going to need to insert a page here. So let me insert a page, because otherwise I'm going to run out of room. Put a page in there. All right, so now let's go to this page and we'll paste. There we go. So you take that 2, one of those 2's, and you put it with the x plus 3 halves, and you take the other 2 and you put it with the x minus 1 half. And then look what happens. When you use the distributive property here, the fractions will always disappear when you multiply it out, and the factors will actually look a little bit different here. Now you'll have a 2x plus 3 there, and this one will be a 2x minus 1. And that's more traditionally the way you see a polynomial like this written, is with factors 2x plus 3 and 2x minus 1. Right? This still gives you negative 3 halves as a 0, right? Because 2x plus 3 equals 0 gives you negative 3 halves. Right? And the same thing here. This works just fine. This gives you 1 half. And you usually see the factors written that way. So generally speaking, if you know that the polynomial is going to have integer coefficients, that's always going to end up working out like that. That will always end up working out like that. All right, so let's see. Kind of recapping here then. We had a polynomial graph. You were given the graph. You take the x-intercepts, and those x-intercepts tell you the zeros that you have for the polynomial. So in this polynomial, the x-intercepts were at negative 3, 0, negative 3 halves, 0, and 1 half, 0. We use that to write down the zeros for the polynomial. Since at one of the zeros, the polynomial looked like a parabola, that one in particular was a 0 of multiplicity 2. And so right away from that information, you can go pretty quickly to that form right there. In fact, I know I wrote a lot of stuff down beforehand, but really you can take the graph and go immediately to that form I just highlighted and not have to write down all that other stuff that I did right there. And then you use the y-intercept, because at the y-intercept the x value is 0, and you use that y-intercept to find that a value in the front. Now if I tell you at the beginning that the polynomial has all integer coefficients, then, or if I tell you that assume the a value is 1, then you can dispense even with that information at the very bottom. So let me show you a problem where that comes into play. I'm going to actually do things a little bit out of order here. let's build a polynomial function with integer coefficients of least degree with the following zeros. So notice you're not given the graph, but you are given a 0 at -2, at 3/4, and at 5 plus I. There's actually one of the zeros is imaginary. Now, this brings into play something else I needed to talk about. This is called the Conjugate Zero Theorem. The Conjugate Zero Theorem talks about imaginary zeros. And the Conjugate Zero Theorem tells you that imaginary zeros always come in conjugate pairs. Now, what that means is, in other words, if A plus BI is a 0, then A minus BI is also a 0. Right? That A plus BI and A minus BI always come together as zeros. So an imaginary 0 never occurs by itself, as long as the polynomial doesn't have any any imaginary coefficients, which we would never be looking at. So they always come in pairs. So in our problem, what do we have here? We have the -2 is a 0 of multiplicity 2. So what does that tell us? That, that x equals -2 is a 0. The multiplicity is 2. And so that tells us that x plus 2 squared is a factor. 3/4 is a 0. And we know that the polynomial has integer coefficients. Integer coefficients just means no fractions as coefficients. And so that's going to tell us, see, we're going to write this, we're going to streamline this process. We're going to say that 4x minus 3 is a factor, right? If 3/4 is a 0, then 4x minus 3 would have to be the factor. X equals 5 plus I is a 0. That tells us that x minus, this looks crazy, but it's true, x minus 5 plus I is a factor. And what else do you know by the conjugate zero theorem up here? You also know that x equals 5 minus I must also be a 0. And so that tells you that x minus 5 minus I is a factor also. So the polynomial here, and we're going to assume that that coefficient of A has been taken care of and that it's a 1. So we don't have to worry about building that at all or finding that. This polynomial would be x plus 2 squared times 4x minus 3 times, and I know this looks crazy, but x minus 5 plus I and x minus 5 minus I. And that would be our polynomial. Now, I would never, ever ask you to multiply that out. I would just ask you to write out the polynomial like I just did right there. And that would be how you'd leave it. All right, so given the zeros and the multiplicity of the zeros, we can write down the factors. And then we wanted to talk about the conjugate zero theorem. And the conjugate zero theorem, right, simply tells you that imaginary zeros always come in pairs, that they always never occur by themselves in isolation. They always come in twos like this, and that they're always in conjugates of each other. So 5 plus I is a 0. 5 minus I has to be a 0 also. As another example here, if x equals 6i is a 0, then that would tell you that x equals negative 6i is a 0 also. And if x equals 6i is a 0, then x minus 6i would be the factor. And if negative 6i was a 0, then that would tell you that x plus 6i is a factor. All right, so that should hopefully, that's as far as we're going to certainly go with imaginary zeros in this context. So I wanted to kind of go back over that again. Excuse me. All right, so let's see where we are here. The next thing I want to talk about, this is kind of the last thing before we kind of go through a big old summary of all these different things going on with polynomials. It's called the intermediate value theorem. And the intermediate value theorem is a way of locating irrational zeros. So for example, in this particular polynomial, what I want you to see is that notice the directions show that the polynomial has a 0 between x equals 2 and x equals 3. And I've actually given you the graph here so that you can see what's going on here. But here's the 0 right here where I put the dot. And that's going to end up, as it turns out in this problem, ends up being an irrational 0. It means there would really not be any way we could use synthetic division to locate that 0 precisely. But we can tell that the 0 is between 2 and 3. And the way we do that, and this is called the intermediate value theorem, is we synthetically divide by 2, first of all. When you synthetically divide by 2, this is what happens. You get, let's see, 2 times 1 is 2, add you get 0. 2 times 0 is 0, add you get negative 3. 2 times negative 3 is negative 6, add you get negative 5. Now that negative 5 is a remainder, but remember the remainder theorem, which we talked about last time, the remainder theorem tells you that that means that 2 negative 5 is got to be on the graph. So here's 2 negative 5, and sure enough, if you look at it, there it is, right there. It's 2 negative 5, that point right there. All right, then you synthetically divide by the other number. We're trying to locate the 0 between these two numbers. So now we synthetically divide by 3. And so when you do that, I get 1 as the remainder. And so that the remainder theorem says that the point 3, 1 is on the graph. Well, not 3, negative 1, but 3, 1. And notice on the graph, sure enough, here's 3, 1 right here. There's 3, 1 right there. And so the idea is this. Notice that one of the graphs, one of the points, the graph is below the x-axis. Right? This point, the graph is below the x-axis. And at this point, at 3, 1, the graph is above the x-axis. So for a polynomial that never has any breaks or tears in it or anything, what's the only way it could go from below the x-axis to above the x-axis? I mean, the only thing that could happen is that somewhere in between it has to cross, right? And that's the only possible explanation here, is that if at one point it's above and one point it's below, that it's got to cross between. So the graph must cross the x-axis between x equals 2 and x equals 3. Now, if you think about it, you wouldn't really need the graph here. All you'd really need to say here is that, hey, at one of those remainders, the value was negative, and at the other one, the value was positive, right? And if that's true, if one of them's negative and one of them's positive, then the only possibility would be that there's got to be a 0 between the two numbers. Because if one of the values is negative and one of them's positive, it means at one of the points the graph's above the x-axis and one of them it's below the x-axis, which means it's got to cross somewhere in between those two x values. And so that's what you're saying here. So if I were to ask you, hey, use the intermediate value theorem to prove that there's a 0 between two values, all you do is synthetically divide by those two values and show that the remainders have opposite signs. If the remainders have opposite signs, there's got to be a 0 in between those two numbers. Now, what you end up doing here is if you want to make so you know there's a 0 between 2 and 3, So then what you do is you synthetically divide, let's say, by 2.5 and 3, and then you gradually start narrowing down that little window where that 0 has to be, and you can actually, as long as you're getting sign changes in the remainder, that you know that there's a 0 between the two numbers you're talking about. So you could actually approximate the 0 to any degree of accuracy you wanted to by kind of going through that scheme over and over again. I'm not going to ask you to do that. I would just ask you, hey, tell me there's a 0 between these two numbers, or prove to me that there's a 0 between these two numbers. And then that would be the way you'd go about proving it. It's actually a very easy problem. You just synthetically divide twice, show that the remainders have opposite signs. Okay. All right, so we are making progress now through our discussion of polynomial functions. So now really the last two things I want to do here is I want to take a polynomial and go ahead and go through the whole process of finding all the zeros for the polynomial and going that route. So here's our polynomial. I want to find everything about this polynomial that we've been talking about. And I'm going to do another example like this. So we're going to go through the whole deal here and figure this out. So remember, going back to what we talked about before, then we would go back and talk about the degree of the polynomial. I would always ask you that. And the degree of the polynomial is 4. The leading coefficient. Remember, when I write the letters LC, I'm talking about the leading coefficient. And that's the coefficient of the 4th degree term. And that's a positive 1 here. And then the end behavior for the polynomial. Now, I've got the graph sitting there, and you can use the graph to help you with this. Certainly, the graph will help you, right? But the end behavior is that the graph is, because it's an even degree polynomial with a positive leading coefficient, it's got to look like a parabola. And so that means that the graph is going to be rising as you move to the left and rising as you move to the right. Notice that does agree with my graph, because look at the graph's end behavior. It's rising as you go off to the left, and it's rising as you go off to the right. So that does agree with the end behavior. And another way to write that would be to say, as x goes to negative infinity, y goes to positive infinity. Remember, going to negative infinity means you're going off to the left. And then as x goes to positive infinity, which means you're going off to the right, then y is also going to positive infinity. So the graph is rising on both directions, right? So both of those are going to be positive infinity in this case. All right, so that's the end behavior. The next thing we're going to list are what we call the possible rational zeros. Now, the possible rational zeros, remember, are just what numbers are possibly rational zeros for this polynomial. And remember, that is the rational zero theorem. And we did talk about that the last lecture. And remember, what you do is you look at the constant term and the leading coefficient, the constant and the leading coefficient, and you write all those factors down for each of those numbers, which is 1, 2, 3, and 6 for 6. Luckily for 1, it's just 1. And then remember how you write this. The possible rational zeros, you take all the factors of the constant and you divide them by each of the factors of the leading coefficient. In this case, the leading coefficient is just a 1, so you're just dividing by 1. And so you just get 1, 2, 3, and 6 back. But then you have to remember that it could be positive or negative, 1, 2, 3, or 6. So those are the possible rational zeros. The next thing you do is you look for the zeros of the polynomial. And you use synthetic division to find these zeros and the graph. So what does the graph suggest here? You've got an x-intercept at -3, 0, and at 2, 0. So the graph suggests x equals -3, x equals 2 are zeros. So how do we prove that? We use synthetic division. Now, also, by the way, notice it doesn't look like there's any other zeros from the graph. But this graph, I mean, this is a 4th degree polynomial. It better have 4 zeros here. And so where are the other zeros here? And so that suggests that the other 2 zeros might be imaginary. So let's have a look at that. All right, so negative 3 is a 0. So we divide synthetically by negative 3. And we better get 0 as a remainder here. So we go through the arithmetic for the synthetic division. And sure enough, we do get 0 as a remainder. So what we've done, what I usually try to do is I write the factorization down as soon as I've found a 0. Negative 3 is a 0. That means that x plus 3 is a factor. And then the other factor has to be degree 1 less. And remember, this is the other factor right here, is that bottom row. And it has to be degree 1 less. So this is a third degree polynomial. And so I've got it factored like that. So I've got it started as far as factoring. And then I do know that, or at least I think that 2 is a 0. So I divide synthetically by 2. Now remember, here's a place you could make a mistake if you're not careful. You divide into the new polynomial, not the old one, not the original one. So this is the polynomial I'm dividing into. Notice that's the new polynomial in this problem. Right, here's the new polynomial, or these coefficients right here. Right, that gives us this factor right here. But it also tells us what we're dividing into on the next synthetic division. So you bring down the 1. 2 times 1 is 2. Add, you get 0. 2 times 0 is 0. Add, you get 1. 2 times 1 is 2. Add, you do get 0. And so now, what do we have here? Our new factorization. Well, we have the x plus 3 we already found. And now x minus 2. And now this last factor is from this bottom row right here. And that has to be degree 1 less. So this has got to be a second degree. And so this is x squared plus 1. And so where do the other zeros come from in this problem? The other zeros come from that last factor. And so we take x squared plus 1 and we set it equal to 0. And sure enough, notice that what happens here, that you solve and you get imaginary zeros because you get the square root of negative 1, and so you get plus or minus I. Notice they come in conjugate pairs like they're supposed to. So the zeros for this polynomial are at negative 3 and at 2 and finally at plus or minus I. Right, and those are my 4 zeros. The x-intercepts, well, we got those from the graph and from the zeros, negative 3, 0, and 2, 0. Finally, the y-intercept. Don't forget the y-intercept should always be easy here. You just set x equals 0. And if you go to the original polynomial and you set x equals 0, the very top of the page there, that fourth degree polynomial at the very top, you plug in 0 for x, and you get negative 6 for y. So the y-intercept is 0, negative 6. And you could also certainly use the graph to help you with that. All right, so this is kind of the process here, laying this out. You're going to have a couple of problems on the test where you're going to have to go through the whole deal here, like I'm doing here. So I wanted to kind of go back through this one more time, and actually 2 more times, because I'm going to do another problem like this. This one probably more involved than what you might see on a test, but definitely talks about the kinds of things that we want to be able to deal with on an exam. This is a 5th degree polynomial, so there's got to be 5 zeros here. So we have a little bit of work to do. All right, so let's go through this. The degree is 5 because of the 5th degree term there. The leading coefficient is positive 3. So, and it's positive is the important thing. The end behavior for the polynomial. Now you can tell that not only from the graph, but from the fact that it's an odd degree with a positive leading coefficient. The graph tells you the graph is falling off to the left and rising off to the right. That's the end behavior. And that's an odd degree polynomial, positive leading coefficient. So as x goes to negative infinity, y goes to negative infinity because it's dropping off to the left, and off to the right, the graph is rising. So that goes to positive infinity. All right, the possible rational zeros. Now this is a little bit more work here. The leading coefficient, the constant is 36. Its factors are 1, 2, 3, 4, 6, 12, 18, and 36. Oh, a lot of them. And then the leading coefficient is 3. Its factors are 1 and 3. So you take all of those factors and divide them by 1, and then you take them all and divide them by 3. And so the possible rational zeros, actually I'll probably write that list right here. You take all those factors and divide them by 1, and you just get that list back. So 1, 2, 3, 4, 6, 12, 18, and 36. And then you take them all and divide them by 3 also. So you get 1/3, 2/3, 3/3 is a repeat because it's 1, 4/3, 6/3 is a repeat, 12/3 is a repeat, 18/3 is a repeat, 36/3 is a repeat. So you don't get very many more. And it's plus or minus all of those. So this is this big long list of possible rational zeros here. And so any zeros for this polynomial have got to be in that list. So if you look at the x-intercepts on this graph right here, you get that that 3 is in the list from that x-intercept. So that looks good. And not only that, but it looks like it's a 0 of multiplicity 2. Now, this 0 right here looks pretty close to 1.5. So you have to look to see if there's a number in the list that might fit that one. And the same thing with this one. That's between 0 and -1, and then this one right here between -1 and -2. So, there's numbers that might fit some of those, and so we have to look at how this is going to work right here and whether any numbers might fit in, and we may have to use fractions to start doing some synthetic division. All right, so from the graph, we think that 3 is a 0, so we divide synthetically by 3. By the way, we also think it's a 0 of multiplicity 2 because it looks like a parabola at 3. So that tells us that 3 is probably a 0 twice. So that's a good start to the problem. Remember, every time you find a 0, this synthetic division gets shorter. So that's good too. So as I go through this, a little calculation here. I get, let's see, positive 12 there, and sure enough, I get 36 at the end, which gives me 0 when I add. So my first factorization is that f of x is x minus 3 times 3x to the 4th minus 7x squared minus 12x cubed plus 14x squared plus, what the heck was I doing there? Let me back up right there. I don't know what I'm doing. I'm getting too excited about the polynomial here. So it's 3x to the 4th minus 7x cubed. Let me erase some stuff here. There you go. Minus 12x squared plus 14x plus 12. All right, so much better. Now I think 3 is a 0 twice, so I divide by 3 again, but now I divide into the new polynomial. So this one should be shorter. So 3 times 3 is 9. I get 2. 3 times 2 is 6. Add, I get -6. 3 times -6 is -18. Add, I get -4. 3 times -4 is -12. Add, I get 0. So now I've got the factorization looking like this. I've got 2 x minus 3's. And then I've got a 3rd degree polynomial here. All right, and so now I have to see what else I think might be a 0 for this polynomial. Right, and so this one right here looks to fit something in my list. It looks like that might be -2/3. So I put -2/3, I put a question mark there. And that is a number in my list. So I'll divide synthetically by negative 2/3 into the new polynomial and see if that gives me a 0. So you bring down the 3. Negative 2/3 times 3 is negative 2. Add, you get 0. That's a good sign. Negative 2/3 times 0 is 0. Add, you get negative 6. Negative 2/3 times negative 6 is positive 12/3, which is 4. And that does give me 0. So now my factorization looks like this. It's x minus 3 squared times x plus 2/3. And then the last factor is 3x squared minus 6. Now that 3x squared minus 6, let me put it right here. You could factor out a 3 out of that. And so you have this factorization. You wouldn't have to have done that, but so that leaves that last factor with an x squared minus 2. And if you see, I factored the 3 out of that factor right there. So the other zeros come from x squared minus 2 equals 0. And so you get x equals, x squared equals 2, x equals plus or minus the square root of 2. And those fit the other two zeros I've got on my graph. This one is at the square root of 2. This one is at negative square root of 2, like that. Those are irrational. Or, yeah, irrational. So the zeros here are at 3, negative 2/3, and plus or minus the square root of 2. And remember, the 0 at 3 is multiplicity 2. And then from there, you could write out the x-intercepts. You've got the x-intercepts from the zeros. The rest of this is easy. We did the hard part now. And the y-intercept is very easy. The y-intercept is just at 0, negative 36 from the original function. Remember, set x equals 0 to do that. Now, I will tell you that this is going to be longer than a type of problem that you'll see on the test, but I did want to write one out that really had a lot of different things in it to discuss as we went through the problem. So this combines a lot of different things. I don't think you'll probably have something, I know you won't have something this involved on the exam. So
I thought you couldn't write imaginaries as x-intercepts.
I don't have any imaginary ones. Did I ever take a square root of a negative number? Now I did have some irrational ones. So I'm glad you pointed that out again, Anne Marie. Square root of 2 is irrational, but that's okay. It's that you can't have i's in an x-intercept, but these are irrational right here. And those do give you x-intercepts, and you can see where they are on the graph. But on this graph, I had some imaginary zeros, and notice those don't occur anywhere on the graph at all. So that's the difference. Does that answer your question?
Yes, sir.
Okay, good. Good question. All right, so the last few minutes of class, what we want to do is talk about rational functions. And what we're going to do here for these last 15 minutes or so is I'm going to give you two graphs. This is one graph, and then we have one on the next page. And we're going to, given the graph, we just want to write down a bunch of information from the graph. That's all we're doing. Right? And so this is something I would ask you on the next exam. I'll give you a graph and ask you a bunch of questions like this. So here, the first question is x-intercept. Is there an x-intercept from the graph? You literally don't make this harder than it is. This is really as easy as it looks. You're just reading where the graph crosses the x-axis, right? And the x-intercept is right there at 1, 0. Now, I would not give you one where you have to do a lot of estimating or anything like that, right? You ought to be able to read it directly off the graph. If it was an estimate, I would be lenient about just making sure that you estimated something that made sense. The y-intercept, and so notice that would be something we'd have to do. The y-intercept is where the graph crosses the y-axis, and that's that point right there. right? And the y-intercept we would have to estimate, it looks like it's at 1/2, 0, 1/2. The vertical asymptote is the vertical line that the graph is approaching from the left and to the right. And the vertical asymptote in this case is this vertical line right here. And that vertical line is at x equals 2, right? That's at the vertical line x equals 2 right there. And so that's our vertical asymptote, is x equals 2. Don't just write 2 down. You're writing a vertical line, so you write x equals 2. The horizontal asymptote for this graph is the horizontal line that the graph is getting close to, right, but never gets to or gets too close to off to the left and to the right. And so the horizontal asymptote is a horizontal line, and in this case, that would be at y equals 1. So you write y equals 1. Remember that the vertical asymptote is always x equals, and the horizontal asymptote is always y equals, because one of them is a vertical line, one of them is a horizontal line. Right, so vertical asymptotes will always be x equals, horizontal asymptotes will always be y equals. All right, now the next 2 questions, don't kind of freak out here. The first one says, as x goes to 2 from the right. All that means is this: if you look at the graph, and if you, let's see, I'm going to pick a color here. If you're getting close to 2 from the right side, notice I've got an arrow right there. That's x approaching 2 from the right side, like that. And then on the other side, it's getting a little bit cluttered now, but as we're approaching this way, we're saying as x approaches 2 from the left, like that. You're literally coming into the asymptote. So this refers to the vertical asymptote in both of these cases. And all it's really asking is, as you're coming into the vertical asymptote from the left side and the right side, what's the graph doing? Is the graph going up or is the graph going down? Right? That's all you're talking about doing. So from the right, the graph's going up. And so what that means is that y is going to infinity. And from the left, the graph is going down like this. And so that means y is going to negative infinity. And so those would be your answers to those questions right there. It's really just asking you, is the graph going up or is the graph going down? Right, so the first one, the graph is going up. And that's from the right side. This is from the right of the vertical asymptote. And then the other one is, this one's going down. And you're talking about going towards the vertical asymptote from the left side of the asymptote. Finally, the last questions, as x goes to infinity and as x goes to negative infinity. That's simply asking, what is the graph doing as you go off and x is going to infinity, or as x is going to negative infinity? And what that is asking always, that question is always asking about the horizontal asymptote and what is the graph doing with the horizontal asymptote. And what's happening? The graph is getting close to the horizontal asymptote as you go off to the right and as you go off to the left. So the answer there for a rational function, the answer is always the horizontal asymptote. Horizontal asymptote here. It's y equals 1. For those questions at the end, the graph is always, the graph is approaching the horizontal asymptote. Now that, we've made a mess on the graph, I understand that, but so we're kind of picking apart the graph as far as how we're approaching things, right, and writing things out. All right, so we have enough time, definitely, so we're going to look at one more example like that. Here's my graph right here. And so let's write down the information we just talked about from this graph. Excuse me. The x-intercepts. So looking at the graph, you've got a graph here at 1, 0. And I tell you what I'm going to do here is let me make a quick, what I'm going to do is I'm going to copy this graph So I have a nice clean picture of it. And then I'm going to go ahead and paste it down below so that you have a clean picture of the graph below, because we're about to make a mess on this graph, right? So there's a clean picture down below right there. All right, so the x-intercepts are at -1 and at 3. So you have an x-intercept at -1, 0, and 3, 0. You're just literally reading those points from the graph. The y-intercept, this is one where you have to do a little bit of estimating, and so maybe that one is at possibly at 3/4, we'll say. 3/4 would be a decent estimate. All I would ask you to do is make a decent estimate, and so this is an estimate right here. If you write it as a decimal, that would be okay. The vertical asymptotes. There's two of them here. There's two vertical lines. There's a vertical asymptote here at x equals -2. And there's another one here at x equals +2. And so you have two vertical asymptotes at -2 and at 2. Notice the graph never crosses those asymptotes. The horizontal asymptote is this horizontal line right here. And that would be at y equals 1. Now I know that y equals 1 was also the horizontal asymptote on the last problem. Horizontal asymptote won't always be y equals 1. Now in this problem, I do want you to note that the horizontal asymptote is crossed. And so it's possible I could ask you, where is it crossed? And so if you look at the graph, there does have a horizontal asymptote, and notice that the graph does cross the horizontal asymptote at the green dot that I just put on the graph. And so it looks like this would be an estimate in this case, but it looks like at about the point 1/2, 1/2, right? That's the point 1/2 where the green dot is. All right, now let's talk about the asymptotes and how the graph approaches the asymptotes. So let's talk about the asymptote at -2. So as x approaches -2 from the left, and as x approaches -2 from the right, those would be the questions I would ask. And what is y doing when that happens? So if you look at the graph, you're approaching -2 from the left and from the right. I'll put this in red. There's from the left and there's from the right. And so what's the graph doing on the left side of that asymptote? It's going up. The y value is going up. And on the right side, the graph is going down. And so as x approaches -2 from the left, y is going to infinity. And as x goes to -2 from the right, y is going to -infinity. It simply means that the graph is rising on one direction, on one side of the asymptote, and falling on the other side. That's all it means. Now we can do the exact same thing with the other asymptote. So let's see, this would be as x goes to 2 from the left and as x goes to 2 from the right. All right, so the first two questions apply to the vertical asymptote at -2. The second two here apply to the asymptote at +2. And it's the same question. What is y doing on both sides? Right, so we are approaching 2 from the left side, and we're approaching 2 from the right side. And so what's the graph doing there? Well, the graph is rising to the left, and it's, on the left side, and on the right side, it's falling. It's doing exactly the same thing as it turns out. So this would be infinity and -infinity also on this one. They don't have to agree, by the way. So don't think that if you have two asymptotes, they always do the same thing. That's not necessarily the case. Okay, so those questions are appealing or looking at or analyzing the vertical asymptotes. Right, the vertical, let's see, let me back that up here real quick. put that one in red to kind of color code it a little bit. So this one's a vertical asymptote at x equals -2, and the next one is the vertical asymptote at x equals +2. All right, and then finally, the horizontal asymptote is the last thing to look at. So the horizontal asymptote is at y equals 1. And so the questions would go like this on that last one. As x goes to -infinity and as x goes to +infinity. Those will always be the questions. What does y do? Right, and what's the y graph do? What's the graph doing? In both cases, I'm going to put this in green here. What's happening here is the graph is getting close to the horizontal asymptote in both directions. Now, one side's getting close from above and one side's getting close from below, but that doesn't matter. In both cases, it's going to the asymptote. So that's just 1 in both cases. And remember, that answer is always going to be 1, like that. All right, well, that was good. So that allowed us to really, we were able to go through and analyze some graphs. Definitely the first set of questions on your exam on rational functions are going to be, how do you write down all this information about a graph? So I'll give you a graph. This would be a very typical question, what I just asked on this screen right here, and then write it down a bunch of information. Now, what we've got left to do for rational functions is, what we need to do now is, how do you take an equation for a rational function and find out all this information. Find out all of the same information. Right. Now, the one thing that's easy to do is the intercepts. And so that's where I'm going to finish this discussion with. The intercepts are easy to find when you have a rational function. This is an example of a rational function here. And the reason why the intercepts are easy is because you do the same thing that you've always done for intercepts. For the x-intercept, you set y equal to 0. For the y-intercept, you set x equals 0. Now notice when you set y equal to 0 in this particular function, you get that function, or that equation, you get 0 equals x minus 2 over x plus 3. You clear the fractions by multiplying by x plus 3, and that just gives you 0 equals x minus 2. By the way, that will always happen. But notice what we were left with was the numerator. And so the good news here is that the x-intercepts are always, for these functions, going to be set the numerator equal to 0. So that's good. And you just get x equals 2. And so the x-intercept for this function is at 2, 0. The y-intercept, you set x equals 0, and you get -2/3. You just do the arithmetic. And so the y-intercept is 0, -2/3. So the x-intercept, you set the numerator equal to 0, and then solve for x. The y-intercept, you set x equals 0. Whoa. Set x equals 0, solve for y. There you go. All right, so next time, asymptotes. That's what we'll do. Next time, finding asymptotes and sketching the graphs. All right, so last thing to mention here is textbook homework. In case, or textbook practice, I'll say that. So on polynomial functions, this is section 5.5. This is page 412 of your book. problems 15 through 45 would be great practice there. And then problems 57 through 65. 57 through 65 would be great practice also. All right, and then on rational functions, we've only talked about the first part of rational functions so far, but there are some good problems having to do with graphs and answering these questions. And actually, I guess I can't find anything out of the book out of that. You will see some problems on the review for that. So I'll just leave it at that for now. So, all right. Any questions, anybody?
Nope, I'm good.
I'm good.
Okay, it's a lot of material, so get some practice in. Let me know if you have any questions. Have a wonderful day. Hopefully, I'll see you guys on Wednesday.